Hey, so we're Group 8. We're doing cardiovascular stents. I'm Kyle.
I'm Rob.
And I'm Darren.
So what's the problem? In the United States, there are a ton of people with cardiovascular stents, and there are a few problems with them. So there are two types of stents. There's bare metal and drug-eluting. And the main problem with bare metal stents is you get something called restenosis, which is scar tissue growth on the stent. And that'll actually close up the blood vessel and cause people to need more retreatment. So they developed drug-eluting stents, which were meant to combat this by preventing any tissue growth on the stent surface. But this leads to thrombosis, which is clots sticking to the stent because there's no tissue stopping them from doing that, and re-narrowing the blood vessel or having the clots separate and go downstream basically and cause problems there.
So our approach is to use a magnesium alloy instead of the typical stainless steel or titanium alloys that are typically used in stents. The magnesium alloys have been shown to have a more beneficial degradation rate of 12 to 24 months, while also having been shown to have comparable physical properties to standard stents that are currently on the market. We also want to seed the inner semi-porous of the stent with a layer of autologously sourced endothelial cells to prevent tissue growth and mitigate the effects of thrombosis. So this just depicts our design with a semi-porous interior and autologously sourced endothelial cells implanted there. The magnesium alloy will have the desired degradation rate to allow an optimum ratio of tissue growth to degradation of our stent, and it maintains the mesh structure for expansion during implantation.
So a few benefits that extend beyond what our desired results are that the use of the endothelial cells may be able to limit other cells from growing on it, which will lower the possibility of restenosis. And the implanted endothelial cells are already integrated into the blood vessel, so it will allow, or potentially will allow, this endothelial layer to grow, which will actually stabilize the stent and stop it from moving, which is another minor problem that current stents have on the market. And the degradation of magnesium alloys can be controlled, so we can control the amount of time that the stent degrades in order to allow the endothelial layer to grow and stabilize itself within the vessel. A few costs that are going to happen with this is that the use of autologous endothelial cells could cause more surgeries for the patient if they can't do everything in one go. And also if the endothelial cells do not promote the cell growth layer that we want, it could open up the platelets and other plaque to actually adhere to those semi-porous structures and cause the same problems that we were trying to prevent. And any increase in the manufacturing costs, whether it be using a magnesium alloy or making the inner surface semi-porous, will most likely go directly to the patient.
So why are we using this instead of other stents? As I stated, the two current stents on the market are mainly bare metal stents and drug-eluting stents. The problem with bare metal stents is they allow tissue growth, but they allow tissue growth of any kind, which can lead to restenosis, because if you have scar tissue growing on the stent, it'll actually wind up closing the blood vessel. And the drug-eluting stents don't allow any tissue growth on the surface, which just leaves an open metal area for platelets to stick to, causing thrombosis and blood clots. So both stents have a problem where they either allow too much growth or not enough, and we're trying to fix that by allowing growth of a specific type of cell to allow the stent to just reintegrate into the surrounding tissue.
Any questions?